we are addressing the problem of where are we in the vaccine. There's been great progress as far as treatment of HIV infection is concerned. Once the virus was isolated and the life cycle was determined, there were many targets which were suitable for development of new drugs. And at this moment, about 25 different um, types of drugs are available to cover nearly every aspect of the virus. There was also initially the problem of too many tablets. In 1990, about 20 pills had to be taken every day. And since 2012, there have been now only one tablet needs to be taken every day. And not only oral drugs, but injectable drugs are also available, which need to be taken once a month or once in 2 months. As a consequence, deaths related to HIV/AIDS have been decreasing, and persons on antiretroviruses therapy have been increasing. Last that I looked at WHO website, it said that since its discovery in 1981, about 78 millions have been infected with HIV. 39 millions have died as a consequence of infections associated with HIV/AIDS, but the incidence has fallen by about 38% since 2001. Every year, 2.1 million become infected, and at this moment, there are 12.9 million living with hearts. $24 billion is what is being spent on HIV. So before heart was introduced, HIV infection would ultimately lead to death. But since various drugs have been available, it has become a chronic disease which cannot be cured, but can be suppressed, and a person can have long life expectancy. There have been four or five cures of persons who have been cured of their viral infection, but mostly that has been after stem cell treatment. And recently, there was also in the news that using CRISPR, you can edit out CCR5 receptors, which are the site where the virus binds to the cell before it enters. And if CCR5 receptors are missing, then either a person is naturally resistant to infection or he can be made resistant. And I think in China, they are offering that in genetically engineered babies to be created without having CCR5 receptors on their lymphocytes. In the 40 odd years that HIV vaccines have been under development, more than 200 different types have been attempted. And we have now come to know that broadly neutralizing antibodies can bind to HIV virus from diverse strains, inactivating the virus. Broadly neutralizing antibodies may not completely block mucosal portal of entry. Beyond neutralization, antibodies may also mediate protection through binding to cognate epitopes on HIV, immobilizing virus in the mucin layer. Antibodies can also elicit immune responses through complement-mediated lysis, recognition of FC receptors on effector cells, and mediate antibody-dependent cell-mediated viral inhibition, including antibody-dependent cytotoxicity, antibody-dependent cellular phagocytosis, and antibody-mediated release of cytokines and chemokines. There have been a number of trials which have been tried initially with antibodies and now with antigens also. About 10 efficacy trials have been reported, and as you'll notice here, most of them have led to failure. The last one was the Mosaic trial, which on 18th January 2023, they found that it has no efficacy. The only ray of hope was the trial which is known as RV144, which was initiated in September 2005, and the reports were available by 2009. This was a two-step vaccine, which was done in Thailand. And after following up for 3 years, they found that the efficacy was at 3.5 years of starting the study was 31%, though at 1 year, that means 6 months after the initial doses were given, efficacy was 60%. So the prime boost, this is a prime boost vaccine, which consisted of 2 components. There were 4 doses of LVAC HIV using recombinant HIV antigens of envelope, gag, and polymerase in canary pox virus for priming, followed by ADVAX containing GP120, which boosted immunity with envelope proteins from HIV of subtype B and E. Over 16,000 adults between the age of 18 to 30 years were assigned randomly to 2 groups and followed up every 6 monthly for 3 years. There was 126 infections with HIV, 74 of them was in placebo, 51 in the vaccine group, indicating that after 3.5 years of follow-up, the protection was 31%. On analyzing those who showed protection, there was a strong association with antibodies that recognize V1 and V2 region of the envelope protein that coats the virus. People who got infected despite vaccination had distinct signature in the V1, V2 region, meaning thereby that vaccine created an immunological barrier. Only in a subset of viruses could break through and cause infection. Follow-up vaccines, which trials were RV305 and HVTN702, and both of them showed no efficacy, so this did not progress further. But in the recent past, as you know, we have just come out of COVID-19 pandemic, in which the vaccines, a number of vaccines which proved to be effective, were formulated in pandemic speed. There were many things common with SARS-CoV-2 and HIV. Both HIV and SARS-CoV-2 emerged as new viruses without specific diagnostic tests, treatment, or preventive modalities, and their initial containment relied on public compliance with behavioral changes to mitigate spread. Both pathogens are RNA viruses with propensity to mutate and diversify, making it challenging to develop interventions, with one important difference that the RNA of HIV is then integrated DNA, it converts into DNA and is integrated into the host, while that did not happen with SARS-CoV-2. HIV research, which made COVID-19 vaccine possible, included rapidly identifying and sequencing a new viral pathogen, new technologies for vaccine delivery, messenger RNA vaccine delivery, adenovirus vector, which we used in India, creation of stabilized COVID-19 spike protein because of HIV structure biology, HIV vaccine field trial infrastructure, strong relationship between academia and industry, and clinical trial sites within US as well as resource-constrained countries, so that once the candidate was ready, it could be tried quickly. Now in COVID, we know that the virus binds to the ACE2 receptors and then gains entry. And vaccine produced neutralizing antibodies, which will which will neutralize the virus and would prevent its attachment to ACE2 receptors. Similarly, the structure of HIV also has is trimeral, and it can be as open structure or closed structures, and there are many antigens which are still under process as candidates for vaccine. What the biggest problem has been that HIV outer envelope protein is a trimer, and the trimer is densely coated with sugar molecules in purple that do not trigger immune response. Most of the surface trimers that are not covered in sugar are highly variable. This is in red and yellow. That would mean that, as we have seen with COVID-19, that if the spike protein antigens change, then neither the monoclonal antibodies are effective, nor are the vaccines as effective as the previous one. A number of monoclonal antibodies, broadly neutralizing antibodies, have been tried, and then they've shifted on to. But now we know that what is required is broadly neutralizing antibodies. In individuals infected with HIV-1, viral diversification of envelope sequences was found to be required for broadly neutralizing antibodies. From this work came the concept of transmitted founder envelopes that initiate the infection and B-cell lineage design, whereby sequential immunogens are chosen from the autologous involved viruses that induce broadly neutralizing antibodies, or are structurally designed to have affinity gradient across maturing lineage members and to select for desired mutations to favor broadly neutralizing development. Broadly neutralizing antibody development follows a jackpot effort where each individual with HIV-1 who makes broadly neutralizing antibodies has only one of very few broadly neutralizing B-cell lineage that has been made it through a torturous process of maturation. In studies of cohorts of individuals positive for HIV-1, those who make broadly neutralizing antibodies have high titers of circulating CD4 T follicular helper cells. Those are known as TFH cells. Low levels of CD4 regulatory T cells and circulating T follicular regulatory cells. So the regulatory cells were lower and there was high levels of follicular helper cells, high levels of plasma autoantibodies and low levels of functional natural killer cells. Increased availability of CD4 THF cells and reduction in the number of functional TREG T regulatory cells and natural killer cells, both of which constrain germinal center responses to reduce autoantibody production, may enable enhanced B cell somatic hypermutation and repertoire diversification. In addition, individuals infected with HIV-1 who make broadly neutralizing antibodies have perturbations in their B cell IgG repertoires such that B cells receptors with longer heavy chain complementarity determining region known as HCDR3S and increased autoreactivity are expanded. Thus, HIV infection results in permissive immunological environment that favors eventual broadly neutralizing antibody development. HIV envelope primers with target for broadly neutralizing antibodies are shown in this slide. A polyclonal multi-B cell lineage response requires development of broadly neutralizing antibodies which bind to CD4 binding site and to at least two other epitopes, such as V2 glycan, V3 glycan patch, fusion domain or membrane proximal external region, Fab diversification glycan antibodies bind to high mannose residue at multiple sites on the envelope. So looking at all this, structure-based immunogen design can be done by determining broadly neutralizing antibody envelope complexes that provide atomic level information that is necessary for modeling specific broadly acting antibodies as template for immunogen design. These immunogens can then inform the modification for improving envelope immunogen binding to the antibodies or precursor. Structure-based immunogen design is utilized to inform all stages of vaccine design. Shaw and colleagues engineered Siamese human immunodeficiency virus, SHIVs, by mutating the CD4 binding site of primary or transmitted founder HIV-1 envelopes to make them more infectious for rhesus monkeys. Remarkably, when SHIVs were constructed with envelope immunogens derived from transmitted founder viruses from individuals who made broadly neutralizing antibodies and used to infect monkeys, the envelope evolution in monkeys was frequently quite similar to envelope evaluation in the human infected with HIV from whom the transmitted founder envelope was derived. A considerable advantage of HIV infection model is that broadly neutralizing antibody lineage can be followed from before induction and throughout the affinity maturation process, culminating with the appearance of broadly neutralizing antibodies. Identification of viral envelope antigens that guide broadly neutralizing antibodies can inform novel immunogen design. And similarly, as the virus was modified, now humanized mice is also available so that the effect of the new antigens can be studied. We know that the problem also is that there is not only one vaccine which can be applied throughout the world, and we know that there are various subtypes which are prevalent in different regions, and they would have to be taken into account. So in conclusion, I can say that development of HIV vaccine is at a crossroad. The failure of Mosaic clinical trial in 2023 and the previous trial in 2021 means that there is no clinical candidate in phase 3 trial at present. However, messenger RNA technology, which has been a great success in COVID vaccine, offer great potential and an excellent platform for any candidate that we might have. But we now know that the candidate must have multiple antigens and it must stimulate multiple B cells so that the effect is production of broadly acting neutralizing antibodies. 3 candidates using messenger RNA are in phase 1 clinical trial. If a person asked when would HIV preventive vaccine be available, given the long history of failure and about 200 odd vaccines have failed, it's hard to speculate when an effective preventive HIV vaccine will be available. However, it is important not to give up. Benefits of a protective vaccine would be immense, though there's been success of pre-exposure prophylaxis, Trovida, which needs to be taken once daily for life, or gene editing of CCR5 in one cell stage for IVF. Still, 1.5 million people get infected every year with HIV. So it's very clear that we need an effective preventive vaccine if we are to eradicate HIV. I hand you over back to
Thank you,
the moderator.
Thank you. That was very good. Professor Yaro is now here, so technology has not won this time. But before we move, would anybody like to ask any questions to Professor Rattan, or we can wait till the end? Okay. Well, yeah, Ibrahim.
Thank you very much, the uncle, and the wonderful presentation by the prof. In a quick layman question, hence HIV has to do with immune suppression, immune depression, or immune compromise, and also the embedding of the HBI gene into the DNA. So, in a summary, is it a clean of the DNA, or how does it function? Is it for the already infected ones or for the non-infected ones? Thank you very much.
I didn't comprehend the question. Sorry.
Okay, sorry, Prof. What I was trying to ask is that, hence HIV is about immune depression, yes, compromise, and also the vaccine of the HIV is it targeting on the non-infected person or both? That's the question. Thank you.
See, there would be two approaches. The vaccine is for prevention. And of course, if a person, so that is before immunosuppression comes.
Yeah.
But once a person is infected, because it's targeting the T cells, so there'll be immunosuppression. But as I indicated, there are 25 different antiretroviruses available and drugs available. Now the drugs can be taken, and instead of taking 20 tablets, one tablet need to be taken because it's available as fixed dose combination. And pre-exposure prophylaxis of a person who's not infected, but it has risk, but he will have to take the pre-exposure prophylaxis every day of his life. On the other hand, there is post-exposure prophylaxis available so that it is possible to suppress the virus, and HIV is no longer a death sentence. But our aim is to prevent infection itself, which is the biggest challenge, and that is where we've been failing. But a vaccine which is effective will prevent the virus and is the one which is required if we want to eradicate HIV.
Fantastic. Thank you for answering that. Could I hand over to Professor Yaro, if you'd like to start sharing your screen?
Yeah.
Fantastic. I will just leave you with the stage, Professor Yaro.
Yes, we can see your slides now, Professor Yaro. Please continue.
Yeah. So thank you very much, Professor Ashok. And I think I'm sorry for my delay. You know, this network, I was supposed to start first. And so during my presentation, I think some of my slides will interface with Professor Ashok. So I'll try my best to, you know, limit whatever I want to say. So, hello?
Hello?
Yeah, okay.
Hi. Hi.
Yeah, hello. Yeah, so we are talking about HIV vaccine. And what we can say is at the beginning of HIV vaccine, actually before then, one of these holy scriptures has this very interesting saying that in the beginning was the words of God, and the words of God was the words was with God. So similarly with HIV vaccine, at the beginning was false hope. When the then US Secretary of Health, Margaret Heckler, stood before the international media on the 13th of September, 1984, and promised the world on the behalf of the scientists that a efficient working HIV vaccine will be available within 2 years. But unfortunately, 30 years plus after, there is still no an effective HIV vaccine. So in medical science, there are normally no rooms for such false hope. So based on that, we can now delve into HIV. Actually, because we are dealing with HIV vaccine, I would not like to go much into the genomic description of HIV. So in brief, what I can say is in 2021, we had 38.4 million people living with the virus, of which 1.7 million new infections were recorded and 770,000 associated deaths were reported. So when you look at the AIDS incident prevalence ratio, which is put at 0.05, it is assumed, which is a correct assumption, that HIV infected people will continue to rise. Currently, we have very effective treatment options. Like we know, currently there is this long-acting antiretroviral drugs that are on the agenda. Then we also have the prospect of coming out with single pills instead of taking these cocktails of antiretroviral drugs. But however, still we need more effective preventive strategies. So in the nutshell, we need a safe, effective, and accessible HIV vaccine. So the question that needs to be asked is, why do we actually need HIV vaccine? I was not in the beginning of Professor Ashok's presentation, but so I don't know whether he briefly may have spoken about this, but in the summary, the use of a combined antiretroviral therapy actually does not lead to the complete eradication of the virus from the body. And normally,
sorry, Prof, please excuse my interjection. Your slides are not moving and they are not on slideshow mode. Sorry for interrupting.
On slide mode. So it's not moving now. It's moving from it's moving from my side.
Oh, maybe it's me only. It's still on the first slide.
No, it's still
No, because
it's still
No, they're not
Maybe
moving.
so.
you can use slide share.
It's everywhere.
Can you see my latest slide?
No, it's on the first
No.
one.
No,
Use
please.
slide share. Use slide share.
Use what?
Slide share from the platform.
I should use what?
It's on the
Slide
title
share.
slide.
Slide share.
Slash.
Share screen. Share screen.
Yeah, he's saying now you are sharing screen sharing. That's what he's telling me.
Yes, Prof, we can see your slide, but you are still in the title slide. It hasn't moved.
I don't know why, because from here on my side, I'm saying, why do we need HIV vaccine?
I still see the very first title, and it's not on slideshow, which is not a big deal, but it's okay.
Professor, do you want to just start again, like cancel the window and then start sharing screen again, please?
Okay, let me,
Yeah. Yeah, and now slideshow.
Can you see now?
We can see your full desktop actually. We just need to see the so if you can go on slideshow, or if you can press I think F5.
Sorry, Shruti, did you just click the slideshow button there, Prof?
Yeah.
Okay,
So
go
I'm
back
coming.
and don't press it and see if you can do it manually. Because I think share.
Are you seeing it now?
Okay, move your mouse. And click on another slide. Click on that. Yep. Okay, please continue your presentation by doing that when you're in slideshow.
Okay.
Yeah.
Thank you.
Okay. So as I was saying, let me start again. In 2021, we have 38.4 million people living with the virus. And out of this, we had 1.7 million new infections, of which 770,000 associated deaths were reported. So based on the incident prevalence ratio, which was put at 0.05, it is suggested that HIV-infected people will continue to rise. Currently, we have very effective drug treatment options, and I think there have been a lot of development, like we're trying to move from the cocktails of tablets that we give out now to single tablets. And also there is this prospect of the long-acting antiretroviral drugs. However, we still need an effective preventive strategy. So I think one of the best preventive strategies will be a safe, effective, and accessible HIV vaccine. Oh. So why do we need a HIV vaccine? Actually, we need HIV vaccine because when we use the combined antiretroviral drugs, it does not lead to complete eradication of the virus from the body. And whenever there is treatment interruption, there is viral rebound. Then we all know about the burden of antiviral drug resistance. And fourthly, term use of combined antiretroviral drug is associated with serious non-AIDS events such as cancer, cardiovascular diseases, metabolic disorders, osteoporosis, and etc. And also when we look at the logistic required for treating people who have HIV and AIDS, due to the limitation and the challenges of course, means that we really need an HIV vaccine. So some will be asking that, what are the desirable attributes of a potential HIV vaccine? There are a couple of them, but let me just summarize them. One, they should be able to elicit long-lasting all-round protection. Then secondly, it should have a limited number of dose administration. Then thirdly, it should be affordable. It should be easy to administer and easy to store without need of cold chain system. And it should be either preventive or therapeutic. I think one of the questions that the non-scientists have been asking us up to date is, why is it that up to now we've not been able to develop an effective, safe HIV vaccine? Well, I think there are a lot of challenges when it comes to HIV development. Number one, like high mutation rate and recombination. Then when you talk of genetic diversity, for example, when you take HIV, it have M, N, O, and now they've added another strain called a P. Even within M, we have different strains, about I think 7 of them from A to J. So all these mitigate against a possible development of HIV vaccine. Then still we are not able to understand fully the correlation of immune protection. Then in the past, there were issues of lack of appropriate animal models. But I think even from Professor Ashok's slides, I've seen one of the prospect of humanized mouse models. So maybe we may be able to overcome that particular challenge. Then next is lack of induction of potent and long-lasting immunogenicity. Then the next one is limited investment by pharmaceutical industry. I call them the pharma tiredness, because they've been putting a lot of money since the 1984s. They've been pushing money, but still there is nothing coming out. So they are definitely tired. Then we can also talk about the safe and regulatory concerns. So based on this, we ask ourselves, is there any hope that a HIV vaccine will be developed? Well, I believe that there is hope. For example, it has been suggested that polyvalent vaccine can be developed. Then also HIV-specific broad neutralizing antibody has given us some hope. Then we can take cue from COVID-19 vaccine, where it was a very huge success, and within just some couple of months, many platforms and which was developed, which subsequently led to development of vaccines. But I don't want participants to go and start quoting me as Margaret Hickler and say, oh, Abubakar Yaro said around the corner there will be a HIV vaccine. Because we know there have been some models which show some responses, but at the end they failed. So there are hope, but it should be an optimistic hope. So if we want to develop a strategy for a potential HIV vaccine, what should we do? What I want we should understand is HIV is not like other viruses. Therefore, empirical design of how other vaccines are developed is not possible for HIV. Because, for example, if you take the whole killed virus as is used in like polio, for example, with HIV, there will be fear of irreversible HIV integration into human genome. Therefore, the best option that we have is rational design based on subunit vaccine. And as Professor Ashok just showed us in his slide, there have been rapid development of molecular biology of HIV, which has led to the development or description of some major structural proteins, which can be used as vaccine targets. However, we have to always remember that genetic variation is still a major obstacle. So in the early phase of HIV, between 1984 to the maybe late 90s, there have been two massive vaccine design models. One was based on induction of neutralizing antibodies, and second was based on stimulation of T-cell immunity to HIV. But I'd not like to delve too much into this design because at the end of the day, all the vaccines that were tried failed. As you can see, we have like vaccine, which was tried in 1987 in Canada, and there was no vaccine efficacy. Then VAS-004, between 1998 to 2002, that one's too, there was no vaccine efficacy. However, there was this very interesting trial, the RV144 vaccine, which was a randomized double-blind phase 3 efficacy trial, which was made of recombinant carinopox vector vaccine. It had two models, the AVAC HIV, which was expressing the envelope gag protease proteins plus alum-adjuvanted ACE-BAS-BE and GP120. So during the trials, the vaccine recipients were given a priming injection at 0, 1, 3, and 6 months, which was on the ALVAC HIV arm of the study. Then a booster injection was given at 3 and 6 months, which they used ACE-BAS-B/E. Well, the results showed that there was a significant vaccine-induced protection, which was placed at 31.2%, although it was lower than the expected vaccine threshold. At least that was the first time that we had a protection up to 31.2%. However, it had one problem, and the problem was the rapid declination in protective antibodies level. So based on the sources of RV144, there was the issue of, there was the plan that, okay, why not they should test whether when there is a booster administration, it will lead to maybe improve immune responses. So those recipients who were given R4144 vaccine, they were compared with those who were given the booster vaccine to see how it works. So there were two types of study. The first one was RV305 phase 2 trials, which was a randomized placebo-controlled double-blind study. The aim was to evaluate late boost with ALVAC HIV or ACE-BAS-B/E. So the question was that does it enhance immune correlation of protection? So another question was, should it be administered alone or should it be in combination? So there were three groups, the ALVAC HIV plus ACE-BAS-B/E, or the ALVAS-BE, then the ALVAC HIV with placebo. So after their study, they found that IgG and neutralizing responses were higher in group 1 and 2. And the boost led to higher antibody titers against envelope antigens. However, antibody response did not increase for second boost. The administration of late boost was not associated with lasting antibody response. So the conclusion was late boosting of to RV144 was safe and well tolerated. Then, based on that sources, they decided to go a bit further, and they initiated the RV306 trial, which was also a randomized, placebo-controlled, double-blind study. It was, undertaken in 3 clinical sites in Thailand. The aim was to analyze the efficacy of boosting with RV144 regimen, and it was given at 12, 15, and 18 months after the initial vaccination. All the groups were given original RV144 vaccination. So their results found that there was no serious vaccine-associated adverse events, and also late boost linked with high plasma IgG binding level against GP70. Then when they look at boosting at month 12, those at month 12, they found that there was no increase in GP120 response. However, when it was extended to 15 months, there was an improved response to GP120D, D11, GP120M, and D11. So based on that, when you compare month 15 and month 18 had significant higher plasma response to GP120 antigen, but not GP70V1V2. So one of the conclusions they came out with, GD4 delay boosting was associated with CD4 functionality and polyfunctional score increase, and also late boosting improved vaccine efficacy. So based on the sources of these RV's trials, the HIV trial vaccine network also initiated some series of clinical trials for them to target different clade. For example, they had the HTVN097 phase 1B trial, HTVN100 phase 1/2 preventive trial, then HTVN702 phase 2B/3 efficacy trial. So the 1 and 2 has some greater immunogenicity. However, HTVN702 had to be stopped because during the trial, they found that over 125 people had new infection. So the conclusion they drew was the vaccine could not prevent the transmission of HIV. So just like other vaccine trials, we came to another dead end. So after that particular failure, because a lot of investment went into HTVN702, there was a call of the requirement to change strategy. So there was this call for adaptive clinical trials. So based on that, a lot of vaccine candidates were made available, with more than 100 vaccine concepts being tested clinically. However, because there were a lot of preventive, like microbicide, like pre-prophylaxis regimen, the HIV vaccine agenda was delayed, and people began losing hope here and there. But later there was interest in passive immunizations, where use of broadly neutralizing antibodies like PG9, PG16, VRC01 showed that it had increased breadth and potency. Also, BNABS showed that it has some protective and therapeutic properties. It was able to reduce viremia, and it also delayed viral rebounds. But the question that need to be asked is, can NABS prevent HIV infection in humans? Because most of the trials was used with SIV. So that's a big question that needs to be answered before we can go further on this particular model. So based on that, some people, suggested antibody-mediated protection studies. So a series of antibody-mediated protection studies have been conducted. The target is CD4 binding site of HIV-1, the envelope. And currently, the idea is, can AMP protect HIV infection in MSM or heterosexual women? So there are a few examples of AMP studies that have been conducted. For example, the HVTN703 phase 2B study, which is a test of the concept strategy. It's a 2B randomized controlled double-blind study. The aim is to test the safety, tolerability, and efficacy of VRC01 and to prevent whether it can prevent HIV infection in healthy, sexual, active, HIV uninfected women. So the participants were given an IV infusion of 10 milligram per kilogram of VRC01 every week, 8 weeks. The study has been completed and we are still waiting for their results. Another one is the HVTN704 study, which is a 2B study. The aim is to analyze safety, tolerability, and efficacy of VRC01 among healthy men and transgender men who have sex with MSM. So they were also given 10 IV infusion of 10 milligrams per kilograms of VRC01 versus 30 milligrams per kilogram VRC01 or placebo every 8 weeks. That one too, the study has been completed and we are still waiting for the result. So currently or whatever, there are some HIV vaccine that based on the current model have undergone some efficacy trials. For example, the Imbokodo study, which is a proof of a concept study, actually is a multi-centered randomized controlled double-blind phase 2B/3 efficacy studies, which involved about 24 sites across some sub-Saharan Africa countries. The aim is to assess the efficacy, safety, and tolerability of prime boosting regimen. And the regimen consisted of tetravalent adenovirus vector vaccine, AD26 for HIV. It was administered via MI at 0 and 3 months, which was followed by IM AD26 mosaics for HIV plus aluminum phosphate aggregated class C GB126 versus 12 months. It was given between 6 and 12 months. Their primary endpoint was assessment of vaccine efficacy, retrogenicity, and adverse events. The second endpoint was immunogenicity, immune response biomarkers, and genomic sequencing of viral isolate from both vaccine recipient and placebo. Initially, it was expected to be completed in September 2023, but the preliminary result has shown that it does not protect women against HIV infection. Then came the Mosaic phase 3 efficacy trial. That one too is a multi-center randomized controlled double-blind phase 3 efficacy studies, which was conducted in Europe, North America, and South America. The aim was to assess the safety and efficacy of AD26 for HIV and adjuvanted class 6 GP140 and mosaic GP140 protein. The participants were healthy HIV uninfected SM, and transgender people. The primary endpoint was assess the vaccine efficacy, and the secondary endpoint was solicited and unsolicited adverse event, whether they will find any. then the envelope-specific humoral and cellular immune responses. So the preliminary results showed evidence of vaccine-induced immune response. But however, the trial was stopped in January 2023 because just like the other trials, they found that it couldn't prevent the transmission of HIV. So the next one was the PrEC-VAC phase 2B trial. That one too was a randomized controlled double-blind phase 2B trial studies, which was conducted in Mexico, Mozambique, South Africa, Tanzania, and Uganda. The aim was to evaluate the efficacy or effectiveness of combined 2 HIV regimen. The regimen was DNA/ACEVAX or DNA/CN5G54GP140 plus MVA/CN54GP140 with PrEP-VAC. 6 groups were identified, and each were either given vaccine regimen or placebo with PrEP. That one too has been completed, and they are waiting for the result. However, the ultimate goal of the study was to find out whether the vaccine will lead to the reduction in HIV prevalence. So these are some of the vaccines that are being in trials, and we are waiting for the result. Although some of them have been suspended because they couldn't show any proof of prevention of transmission of the virus. So to conclude, we can say that development of safe and effective HIV vaccine is a formidable scientific challenge. However, some encouraging results has been reported. When we take cue from COVID-19 vaccine and other vaccine models for cancer, we can still develop some hope that there will be an HIV vaccine very soon. However, we hope the pharmaceutical companies will continue to show interest in HIV vaccine research and development. And we can sincerely hope to have an effective, safe, and widely available HIV vaccine very soon. But we need to surmount some of the challenges like low immunogenicity and genetic variation. So these are the references, and I would like to thank all members of the Team AHRO guys for their hard work, and thank you for listening.
Thank you very much, Professor. That was fantastic. First of all, any questions? If so, then you can raise your hand or just chime in. Ibrahim?
Okay, thank you very much, Prof, for the wonderful presentation and the historic event of our HIV vaccine development. But your last statement in the slide, the recommendation, you talk about the homogeneity or low homogeneity and what? Please, can you elaborate on that?
Yeah, most of the studies that have been, conducted at the end of the day, because the reason why they found that it was not useful, let me use that word, was because the immunogenicity that was generated after the vaccine had been administered to the volunteer led to generation of very, very low antibodies. So if you are able to find a way that we can surmount that low immunogenicity, I think we are on the right course towards developing HIV vaccine.
Okay, anybody else? Prof, sorry if I absolutely butcher your name, Zilangili? Please.
Yes, thank you very much, Prof. Thank you for a very informative talk. Mine is just not necessarily related to the presentation, but you spoke about a humanized mice model.
Yeah.
Has there been any studies, vaccine studies particular in humanized mice model. I just share in South Africa at the beginning where there was a huge, huge trials on microbicides and also some of the vaccine trials. What we observed, people particularly, how do I put it, less educated, once they get into the trials, they get a false sense of security going around saying, no, HIV won't affect me now. I've been vaccinated. I can stop using a condom and so forth. So that's why I'm coming from to say actually humanized mice models, although not so close. And I mean, they would actually play a huge role. Essentially, has there been any work started and preliminary results available? Thank you.
Yeah, I think so far the studies, I have not come across any studies that use humanized mouse model. I think it's in the pipeline. I don't know whether Professor Ashok has a different version to what I'm saying. But so far, from what I've come across, I've not seen any humanized mouse model yet. And you raise another point, which I think we need to add to potential HIV vaccine, should I call it advocacy, where people after receiving the vaccine have this sense of hope, as is rightly said, and say, oh, I will never get HIV, or I will not be able to transmit HIV. I think we need to develop a certain policy that will take care of that. That at the end of the day, we have so many, even currently, after the development of any effective vaccine, we still have a challenge of dealing with these circulating recombinant forms. So there's that possibility. Like in Africa, we know that one person may be harboring more than 3, 4, 5, 6 recombinant circulating forms. So we have to, develop policies against all these false hope here and there. But I don't know about the humanized mouse model, whether Ashok has anything to add.
Yeah, I think it's more for use in the lab to find out how a person will respond. And as you know, we've been struggling up till now to find out what antigens will work now that we know that CD4 is required, V1, V2 is required. And that means the antigens have to be multiple. They're not one antigen which is going to work. And the antibodies also have to be multiple. That means monoclonals will not work. You have to have broad spectrum coverage. And I think as they get into narrowing, and these antigens keep varying. So it's not one antigen which can be fixed. Even in the V1, V2, the epitopes will change. And that means what they're hoping is when they have the repertoire ready, they would be able to try out various combinations in humanized mice model as well as the SHIV model, and then see how it goes. So it's still a work in progress, but there's no study indicating the vaccine has worked in humanized mice.
Fantastic. Anybody else? I saw a hand go up from a Stanley. I don't know if you still want to ask a question. Perhaps not. Any more questions? No? Okay. Well, as a sort of closing statement, feel like I should advertise, if you can just see up there, our next webinar with Umar Ibrahim, actually, who is here. If you'd like to say anything about it, Umar, then by all means. But if not, then please catch us then on 31st of May, I believe it is. All the information is on LinkedIn, social media, Instagram, social media. Make sure to follow us on that. What we like to do, Professor Yaro, if I can ask you to stop sharing your screen.
Oh, yeah, okay.
What we like to do is take a little screenshot of everyone here. If if people are keen on putting their cameras on, and then we can put it on our social media. If you're not comfortable with it, then that's fine. But there we go. See some cameras coming on. Okay. Anybody else? Oh, good. This is a good turnout. Last time when no one was keen, but this is better. All right. Okay. Okay. I'm going to take a screenshot on 3, 2, 1. Okay. Well, if there's nothing else to say, then I think that is us. Thanks everyone for coming. And hopefully see you next time. All right. Goodbye.
Yeah, thank you. Yeah, bye.